machine learning algorithms are being built into tools that are increasingly easy to use. 5 years ago, a developer would have had to write her own k-means clustering algorithm, or her own random forest modeling algorithm. Today, using a complicated algorithm can be as simple as making a function call. On Software Engineering Daily, we've covered TensorFlow, Spark, and other software libraries that are empowering developers with higher-level abstractions to perform machine learning. In this episode, we talk about Keras, a deep learning library for Python, and we explore the long-term effects of machine learning. But first, we're going to hear about one of the sponsors that make Software Engineering Daily possible. You don't have to settle for a job that makes you unhappy, and you don't have to go through the pain of searching through millions of job listings. Hired.com brings job offers to you, the engineer. Hired is a job marketplace built for the engineers. A few years ago, I was unhappy with my engineering job. I felt stuck, I felt underpaid, I felt alone, and I didn't know my value in the job marketplace. It's a very opaque market. So I used Hired.com to find a new position. Hired connected me with a talent advocate who guided me through the process, like a free concierge. They made me feel valued. It was like a white glove service. And this talent advocate helped me with all the questions I had. Should I ask for more money? Should I consider relocating to try to get a higher salary or a better job? The talent advocate that you get paired with on Hired.com helps you with all these kinds of questions. I got several job offers, and I found one that was a good fit. In fact, engineers who use Hired.com get an average of 5 offers from great companies like Facebook, Uber, and Stripe, and the companies are bidding on you to try to get the best engineers, and so you end up with the higher salary. Go to hired.com/sedaily for a $4,000 bonus upon signing up. It is completely free to engineers looking for a job. I've interviewed the founder of Hired, Matt Mitchkovich. He also started 99 Designs and SitePoint. He's a software engineer, and he understands that engineers deserve the leverage in this super competitive market where great engineers are at a premium. Check out hired.com/sedaily. I'm happy to advocate Hired to my listeners because it puts power in the hands of engineers. Now let's get on with this show. Keras is a deep learning library for Theano and TensorFlow. François Chollet is an engineer at Google and is the author of Keras. François, welcome to Software Engineering Daily.
Hi, nice to be here. Very excited to do this podcast.
So before we get into Keras, tell me about your background in machine learning and how you got interested in the area.
So I've been doing machine learning since 2009. But more generally, I've been interested in neuroscience since I was a high school student, actually. So back to 2006. So I don't know. I was just a big sci-fi fan as a kid, and I always thought it would be cool to build robots, right? And so that got me interested in solving the problem of intelligence. Like it seems maybe a bit silly to say, but at its core, that's what it's about. And so I initially tried to study neuroscience, hoping it would help me answer these questions, right? Like, how does the mind work? How do we build a mind? And it turns out neuroscience doesn't really have any of these answers. So after a while, I turned to something called developmental cognitive robotics, which is kind of a subfield of robotics that deals with trying to simulate, so building robots that learn as a human child would, that kind of simulating the early stages of human life. So, and after a while, I kind of dropped out of it, and I just, got into applied machine learning because it pays the bills, right? So I did machine learning at a couple of startups, and I eventually wanted to start doing research again. So that's why I joined Google.
So the movement from neuroscience to to machine learning is interesting to me. So was there a point at where you, because like, so I studied biology for a while, and there was a certain point where I was like, it seems like we just don't understand biology beyond a certain level. Like, speaking about neuroscience, we can talk about how neurons work and how action potentials work, but at a certain point we're kind of guessing. Is that the conclusion that you came to when you wanted to move towards a more deterministic field?
So my impression of neuroscience is it's just about describing, how the brain works at a very basic level, but it doesn't really explain anything. And if you just observe the brain, so the brain is, a bunch of biological processes, and these processes encode information. But if you do not approach the brain from the standpoint of information, if you're just trying to look at these low-level processes that encode information without, trying to move higher up, then you're not actually getting anything out of this observation. So, which is why I find the opposite approach more interesting. So starting from nothing and starting from the information process and then trying to encode them in a different way, right? So instead of starting from like the code and moving up to the first principles, you start from the first principles and you move down the code.
Okay, so it sounds like you don't put much esteem in the way that the human brain processes information. It's just a means to an end to the way to process information, and whether we're processing that information using our bag of water attached to some neural processing that we have biologically, or we're using a computer with CPUs, it doesn't really matter. What's important to you is the higher level informational processing strategies and components. Would you say that's correct?
Yes, absolutely. So I don't think there's anything special or magical about the brain, right? It's just an information processing system. And there is no reason to believe that it's the only reasonable or, the one optimal information processing system to, the only way to build intelligence. So I definitely think we can try to abstract away the first principles of intelligence and then try to go from these principles to an intelligent machine that might look nothing like the brain.
Mm-hmm. So you work at Google now, and yeah. I'm curious if the views that you just explained, are those shared by many of your colleagues at Google?
Yeah, I think that's a pretty mainstream kind of approach to the philosophy of the mind among machine learning researchers. That sure, it's that biology basically should only be used as a source of inspiration, but that we should not try to just copy what it's doing, right? That we should instead try to understand in a very abstract way, the principles of intelligence, and then build our own thing. So I think an analogy would be if you want to make a flying machine. So instead of observing birds and trying to build an artificial bird, instead you should try to understand the first principles of flight. So things like fluid dynamics, and then build kind of a theory, which would be in physics just fluid dynamics, and then use this theory to build a more efficient flying machine, which would be nothing like a bird, more like a plane.
Sure. So, okay, we've talked about machine learning kind of in the abstract, and I want to start easing into a conversation about machine learning in practice. So machine learning is increasingly important at engineering companies, and the old model of software engineering was mostly divided into the roles of people like software engineers, and then you had QA engineers, and you had software development managers. But I get the sense that the rise of machine learning has changed this because you need a wider variety of specializations among engineers, and you start to get these roles like data scientists and data engineers. So before we start talking about Keras, the library that you've built, tell me about how you see the structure of teams in software organizations changing to accommodate the evolution of machine learning as being a critical component of an engineering organization.
So I think most organizations, specifically startups, which are the big employers of data scientists these days, they don't really get it. So people tend to put too much focus on machine learning, but it turns out, like algorithms, but it turns out if you want to solve business problems, machine learning, the machine learning part is actually a tiny part of the solution. So applied machine learning at startups and so on, it's mostly about formulating the right problem, asking the right questions, defining the right metrics that will be tied to business goals, and then collecting the right data to answer these questions and so on. And at the end of the day, the amount of time you spend actually building a machine learning model to solve your problem is tiny compared to all these other things you have to do. And which is why, so the role of a data scientist tends to be more like, sometimes they say it's more like the role of a janitor in a way. So you're like taking care of collecting this data, cleaning up the data, and so on. And at the end of the day, you spend very little time modeling the data. So
interesting. Okay. Well, so a company like Google is trying to bake machine learning into all of the consumer applications. And sometimes machine learning is easier to develop in the lab than it is to deploy into the wild. What are some best practices to deploying the machine learning models that data scientists develop to production systems?
Best practices. Well, I think one big gotcha is when the data set you're using to train your model differs in some way from the data you're going to be applying your model to in production. So it can happen a lot. So especially if you have seasonal data, like imagine that you want to predict ad clicks and you collect data for one quarter, and then you build a model, and then you apply it to the next quarter, and the results might be completely wrong, right? And another example is if you're trying to predict fraud, for instance. So you look at buying activity on an e-commerce website, and you try to predict which sort of activity pattern is indicative of fraud. But the problem is that fraudsters are updating their techniques constantly. So if you train a model at a certain point in time, and then you apply it later, it's not going to work. So you have to keep your model updated, in real time, which is very difficult to do. So I think if you can ensure the proper match between the data you were training your model on and the data you're going to apply your model on, then you should be doing fine.
And so, one of the ways that I've talked to people about how to potentially alleviate some of the problems associated with deploying machine learning is testing machine learning models. Do you have any ideas for how people can test their models? Because I think of this as a difficult challenge when you're essentially trying to test against a data set that is evolving and changing over time.
Yeah, so it's it's difficult, because even if you do forward testing, so basically just running your model on production data for a while, but without actually deploying your model to production, it can be very difficult to draw any conclusions to what you're seeing. So one example would be trying to predict the stock market, for instance. So which is very difficult because if you find any signal in the noise over the past 3 months, for instance, maybe somebody else is going to notice it and start arbitraging it, and then the signal is going to disappear, right? And so there's no like, basically it's a difficult problem. There's no way to be sure that your model is going to work, right?
Sure, no silver bullet.
Yeah.
Okay, interesting. Well, so I want to start easing towards a discussion of Keras, and since Keras is a deep learning library, I want to start with kind of an overview. What is deep learning? How do you define it?
So deep learning is the notion that you are going to model some information space as a hierarchy of features, and this hierarchy is going to be deep, which means it's going to have more than 3 or 4 layers. So for a very long time, machine learning has been mostly shallow, which meant first a manual feature engineering step. So you take the data and you extract some handcrafted features that characterize best what you want to get from this data, and then you train a model that maps directly these handcrafted features to predictions. And deep learning replaces this model with the notion as you are going to learn your features instead of handcrafting them, and you are going to learn more than just one layer of representations. You are going to learn multiple successive layers of representations. And so which allows you to model much more complex spaces much more accurately.
So would you also describe this as a movement from supervised learning, where humans have to be in the loop, to less supervised, like unsupervised learning?
So supervised and unsupervised are terms that have a very specific meaning in machine learning. So usually it's a difference between training a model against labels and training a model that learns to reconstruct its training data instead of trying to predict some label. So I think it's definitely a move from more humans in the loop and more kind of hand tuning in the loop to less of that. So it is kind of, so the dream of deep learning is very much to be able to just plug a model into any kind of random data and get results out of it, right? Without the need for any feature handcrafting and so on. And to some extent, it's been succeeding pretty well.
What are the bottlenecks to even greater success? So
in deep learning, I think the big bottleneck is that nobody really understands why deep learning works. So deep learning is it's a very practical field. So we have techniques that we know work, but we don't really know why they work. And so it's kind of like alchemy,
like neuroscience.
It's I guess you could compare it to neuroscience. So the way research proceeds is that you try a bunch of things, and then you throw a lot of spaghetti at the wall, and then you look at what sticks. And when something sticks, you usually don't know why. So once you notice that something works, you're happy, and you come up with some hand-wavy explanation of why it might work, but usually it's not accurate. So, and the fact that we do not have any solid theory of deep learning is really slowing down progress, because it means we have to, instead of designing a more efficient solution, we have to kind of brute force the space of solution until we find something. One example is just trying tens or hundreds of different convolutional neural network architectures, and until we find something that's better than the previous state of the art. And instead of that, if we had some theory, we could just kind of predict what is going to be the best architecture.
Well, certainly in an ideal world, we would have that. But is it possible that we need to just make a paradigm shift to saying, we're going to have to be satisfied with not understanding what this underlying engine is doing, and we're just going to leverage the increasing hardware capabilities and continue to take advantage of brute force mechanisms? Is there anything fundamentally wrong with that?
I think it's not. There's nothing fundamentally wrong. I mean, it works. This is exactly the way deep learning has been working. And deep learning, it's been this huge a success because it does solve problems, right? We don't really know how, why, but it does. And so there's nothing wrong with that. But I think it's not a very efficient way to make progress. So my impression is that right now we're still making progress very fast without having any sort of solid theory of deep learning. But at some point, it's going to stop. So, progress is usually sigmoidal. So you start slow, then you have this big explosion of progress. And then at some point, you're gonna hit a bottleneck. Progress is going to slow down. And we are not yet at that point where we have stopped making progress. So we're still making very fast progress without really understanding what's going on. But at some point, we will reach this bottleneck. And probably the only way we will be able to go past it is by coming up with a theory of deep learning.
Okay. So as you mentioned, the models that you construct for deep learning are composed of layers. And Keras features an interface to dealing with these layers. Could you talk more about what a layer is?
So a layer can be understood as one level of representations of your data. So one level of abstraction. So a layer is like a unit, like a kind of function that transforms some input data into some projection of your data on some feature space at some level of abstraction. And so deep learning is about stacking these level of representations. So typically you will see increasing abstraction as you stack layers.
Okay, so as you said, layers get composed into this sequential model, the series of layers. Could you give me an example of how several layers could be organized together to represent a useful model?
Sure. I think the classic example for deep learning is the convolutional neural network, which you use to classify images. And the basic example that you have this stack of convolutional layers, and the first layer is gonna learn. It's gonna be an edge detector. So it's gonna learn to detect basically edges in small patches of the input data. And the next layer is gonna learn more complex patterns that are made out of these edges, and so on, until you end up with things like digits or letters.
Okay. That's a great example. Okay.
Yeah.
So what types of tools and programming languages are engineers using to write these neural networks, these models?
I think the big winner in terms of languages is Python. So most people are working with Python today, which is being reinforced even further by the open sourcing of TensorFlow from Google, right? So if you want like an overview of the main deep learning frameworks, there's one that's being maintained by Facebook mostly, which is called Torch, which is written in Lua. It's been quite popular for a while. Otherwise, there's Theano, which is this was the framework for which Keras was initially developed. It's written for Python, and now there's TensorFlow, which is also written for Python.
I love being a software engineer because of how easy it is to build side projects, and I've built countless side projects. I've built a social gambling application, a dating website backend that had 0 users, a stock trading music rhythm application for Android, and I think every developer should have side projects. So when I have a web app that I want to deploy and share, I want to show my friends my most recent project that nobody will care about, I use DigitalOcean to quickly spin up a server and host my projects. And who knows, if one day one of my apps takes off and goes viral and people actually do care, I can easily scale using DigitalOcean's flexible pricing plan. Companies like TaskRabbit that have grown rapidly have used DigitalOcean for this very reason. But until this happens, I will happily stick with the $5 a month plan. Sign up with promo code SEDaily to get a free $10 credit as a listener of our show and start building your apps. We would love to see what listeners build, so send us an email showing us your project. I've also interviewed Moisey Uretsky, who is the co-founder of DigitalOcean, and he mentioned that the ease of use and the flexibility is why they built the service in the first place. That DigitalOcean interview is one of my favorite episodes. Moisey talks about bleeding in a data center. He says, you don't know how hard it is to do a cloud hosting service until you've bled in a data center. It's really interesting. So speaking of which, let's get on with this episode of Software Engineering Daily. So with that in mind, let's get to talking about Keras, which is a Python deep learning library. What is Keras?
So Keras is this. It's kind of is this very modular, very simple framework for building deep neural networks, basically. And it was originally meant as kind of a Python version of Torch. So Torch is this Lua framework that has very nice API, but that is quite annoying to use in large part because it is written in Lua. And so I wanted to make a Python version of this, and it ended up diverging quite far from Torch. So really it's a library that's focused on speed, but not really like runtime speed or compilation speed. It's really about experimentation speed. So you should be able to use Keras to prototype a deep learning model very quickly in like minutes.
Sure. So, okay, so developer efficiency is one of the focuses of Keras.
Yes.
So as you were writing it, were there certain times where you were kind of writing it initially as a rewrite of Torch or a remake of Torch, perhaps? What were the points where you felt you were deviating from the functionality that Torch was written in? I mean, obviously, it's a different language, so you're going to change certain things from Lua to Python, but there must have also been certain design calls that were not really related to the language change.
Yeah, so I think the two big differences are the way, first, the way recurrent neural networks are being handled, and the second is the way that graph networks are being handled. So the very first thing I wrote in Keras was a sequential model, and I wrote it with essentially the same API as Torch. But everything else started, deviating quite a bit. And I think one of the reasons why Keras got very popular very quickly is because it was, when it was launched, one of the only libraries for Python that had good support for recurrent neural networks. And at the same time, there was this explosion of popular interest for recurrent neural networks. Things like being able to generate text, sequences, being able to answer natural language questions, all these kind of problems.
Sure. Okay. So as you said, one of the big motivations was this ability to prototype quickly or perform fast experimentation. Why do neural network developers need to be able to perform fast experimentation?
So the basic reason is because we don't really know, we can't really know in advance if a model is going to work because we don't really have a good theory of deep learning. So the only way to evaluate a model is to actually build it and run it. And so you want to be able to experiment with a wide variety of model architectures very quickly. And this is what Keras allows you to do. So one example is, let's say you build some model with some architecture, and then you want to test a few loss functions. While in Keras, you just have to change one line to test a different loss function in your model.
Okay, that makes sense. So Keras has some guiding principles which define how you have developed the project and how you continue to develop it. And I want to go through these because I think they're an interesting case study, not only in Keras, but in why it's important to have these guiding principles around a project. So the first guiding principle you have is modularity. Why is modularity important to a deep learning library?
Well, deep learning can be understood as essentially plugging together layers, which are, these basic information processing units, turning some inputs into some different output, which is typically a representation of your input over some feature space. And so you really want to make you really want to be working with a framework that's kind of like a bunch of Lego blocks, right? And each Lego block is going to be like, for instance, a layer or maybe a loss function, or a weight constraint or whatever. And you want to be able to just plug these blocks together with as few constraints as possible. And because then you have freedom to experiment, right? And so, modularity.
Okay, that makes sense. So a developer should be able to combine like standalone models to create new models. Could you give me an example of how models could be composed together?
Sure. Let's say you've built a vision model, so something that's capable, for instance, of classifying pictures. And you've also built some model that's capable of generating text. And you can combine these two to create, for instance, an image captioning model. So a model is going to look at a picture and it's going to output some text describing what's in the picture. So this is a classic example of model compositionality. So you train one model separately, it's vision model, and then you can plug it into a larger architecture, and it's going to be capable of more.
Sure. Okay. That makes sense. So Charis is also built to be what you call minimalistic. How do you impose minimalism on the project?
So minimalism basically means that your code should be clean, your code should be short, your code should be very modular. So each function or class should be kept short and readable. So this is very important because if you really want freedom to experiment, you should also have freedom to go look at the code and modify it, right? So I feel that is very important. So especially for researchers using Keras who want, total freedom to adapt Keras to whatever they want to do. So when you build a framework, it's based on some assumptions. And these assumptions, there are constraints for users, right? And sometimes you want to do something outside of these assumptions. So you want to get rid of these constraints. The only way to do this is to go dive into the source and modify it. And if you do not follow this principle of minimalism, you might end up with source code that's bloated or that's difficult to read, difficult to follow. And this is a big obstacle for anybody who wants to modify the framework itself. And I feel the ability to modify the framework is part of the feature set of Keras.
Okay, that's very interesting. So Keras has two models. One is sequential, where you make a linear stack of layers, and the other is the graph, where you have a directed acyclic graph of layers. Which cases do each of these models make sense in?
So I believe most users are only going to be using the sequential model. Sequential model is really about mapping one input to one output. But in some cases, you might have, for instance, several different inputs. So let's say, for instance, you're building this image captioning model. So you're going to have, when you train your model, you may have one input that's going to be a picture and one input is going to be some text, right? So in that case, you might want to use a graph. So typically, you're going to use a graph when you want to map a single input to a single output, and you're going to use a graph when you have multimodal inputs and outputs.
Okay. How does Keras interface with the GPU?
So Keras is built to be able to run on top of either TensorFlow or Theano, which are tensor manipulation libraries that can compile to C++ and CUDA. And so Keras uses these libraries to do tensor manipulation. And then these libraries are going to output some CUDA code that can run on a NVIDIA GPU. So Keras doesn't really handle any of that itself. It's just relying on these underlying libraries.
Okay, so that brings us to kind of a discussion of these tensor libraries. As you said, Charis, by default, uses Theano as its tensor library. What is a tensor?
So a tensor is just a multidimensional array. So if you know what a matrix is, which is like a table of numbers, you can think of a tensor as a higher dimensional version of that. So for instance, a 2D tensor is a table of numbers. A 3D tensor is more like a cube of numbers, and so on.
Is a tensor the means of passing data between layers?
Yes, absolutely. So in Keras, the input and output to any layer is always going to be one tensor.
Okay, interesting. So what is Theano, and how does Keras, like if you use Theano, how does that compare to using Keras with Theano?
So Theano is on the ladder of abstraction. I would say Theano is lower level than Keras. So Theano is really about directly performing math operations over tensors. And meanwhile, Keras is about manipulating basic blocks, which are already pretty advanced things, basically, neural network layers. So it's higher up on the ladder of abstraction, basically.
So Software Engineering Daily did a show about TensorFlow, which can be used in place of Theano. Why would a developer want to use TensorFlow rather than Theano?
So I think currently TensorFlow might not perform as well as Theano over a number of points. So TensorFlow has some performance issues, and it does not have all of the features that Theano offer, but that's because TensorFlow is still very young, very new. It's only been released a few months ago. And I think one motivation for using TensorFlow would be that TensorFlow is backed by Google. So you have the guarantee that it's going to get better over time and probably quite fast. So I wouldn't be surprised if 1 year from now, or even, sooner, TensorFlow would have more features than Theano, specifically things like running in a distributed setting. And it might also become faster.
What are your impressions of TensorFlow? I assume you read the paper. What do you like about the project, and where do you see it going?
So my impression of TensorFlow is that it is like a more mature version of Theano, even though it does not yet perform at the same level because it's not quite as optimized as Theano, but it will become, probably even better optimized in the future. So the one thing that's very interesting about TensorFlow is that it's built from the ground up to be able to run in a distributed environment. So, which is not something that was very easy to do in Theano.
Okay, interesting. So, speaking of that, how difficult is it to use Keras in production? What are the challenges that developers face?
So, I haven't heard much about developers using Keras in production. I know there are some, but really Keras is meant as a prototyping library. So I would not necessarily recommend using it in production.
So what is the migration path from a prototyped Keras model to a production model?
Well, one thing you could do is I think TensorFlow is very suitable for serving a production model. So the path would be you would prototype, develop, and train your model using Keras. And once that's done, you can save out of Keras the computation graph in TensorFlow of your model, which you can then serve standalone.
What are some other projects and libraries that work well with Keras?
So let's say that you're using Keras on top of Theano, then you can probably interface it with any other Theano-based library. So one Theano-based library that's quite popular is called Lasagne. It's used quite a bit on Kaggle. I don't know if you've heard of Kaggle.com.
Sure, absolutely.
Data science competition website, yeah. So because both these libraries would be based on Theano, so they would be manipulating the same tensor objects, so you could interface them.
Okay, interesting. So maybe this doesn't fit into the conversation, but would you want to use some of the newer streaming frameworks like Spark or Storm with Keras, or is that totally orthogonal?
It's not completely orthogonal. So there is actually a project on GitHub about using Keras in a distributed setting with Spark. It's called LFAS, ELEPHAS. It's made by a company in Germany. So it's you can definitely run Keras on top of Spark using this project. So the general idea is that you're going to replicate a Keras model on several nodes, and just do distributed training.
So is that kind of like you take a Keras model and then make it into an RDD?
Yes.
Interesting. So I've done some shows about libraries that were written for prototypes, and I think what I find a lot of times with prototypes is that people tend to turn them into like the thing that starts as a prototype ends up being a full-fledged application. But maybe that's not something that is prone to happening in machine learning. Could you see Keras becoming something that people actually build production models knowingly in?
I think it's already happening. It's not necessarily something I would recommend, but it's clearly happening. Yeah, I know. Since now you can use Keras on top of TensorFlow, I don't think it's a big issue. I don't think Theano was very much production ready, but TensorFlow definitely is.
So what is the future of Keras? What's the roadmap?
So we're just going to continue building out the feature set of Keras, improving code quality, improving documentation. One thing that we definitely want to do more in the future is provide more examples, tutorials, how to use Keras to solve problem X, problem Y. And one thing we want to add is a library of pre-trained models that you could load with Keras. So instead of having to train your own model from scratch, you could just download one and then fine-tune it to your problem.
Okay. So many of the engineers who listen to this show have probably only a loose understanding of machine learning, and they spend probably most of their time writing just kind of day-to-day business logic, maintaining their applications and so on. But I'm sure many of them want to know more about machine learning, or they at least want to get a basis for what they need to understand about machine learning going into the future. What are the concepts? What are the basic machine learning concepts that engineers that may not necessarily be working on machine learning, but they need to? What are the things that they need to know to stay up to date with the way that our field is changing?
So, well, it depends if you want to understand machine learning. or if you just want to use machine learning. I think you can use machine learning without necessarily understanding it. One example would be a very popular machine learning library, scikit-learn. So you can definitely use scikit-learn to solve data science problems without really understanding the underlying algorithms, right? As you gain experience using it, you will start gaining some intuition about the properties of each model. But you do not even need to understand what these models are really doing in the background to develop this intuition. So if you're interested in really understanding machine learning, then you should start understanding linear algebra. And then you should go from there to implementing your own basic toy versions of popular algorithms, things like logistic regression, random forest, some neural networks, and so on. So I believe implementing your own algorithms is key to understanding what they're doing. So that's one thing. And if you just want to use machine learning to solve problems and you don't really care about understanding how it works, then the best thing to do is to use one of these very high-level, easy-to-use frameworks like scikit-learn or even Keras.
You mentioned linear algebra. Why is linear algebra so important?
So because what you're doing, for instance, deep learning, is just manipulating tensors. So lots of tensor multiplication and so on. And these tensors, they're encoding points in some vector space. So if you want to develop an intuition about what's going on inside your network, you definitely need to have these mental models that come from linear algebra.
From your experience working on Charis, what have you learned about writing developer tools, or specifically open source developer tools?
So I've learned that open source can be very frustrating sometimes. You release something and it can be very overwhelming when the project becomes popular because you get so many support requests. And one thing that you have to understand early on is you have to learn how to say no to feature requests and support requests and so on, because this is what is going to allow you to keep focus, to stay focused on making the library progress, making the project progress. And you cannot, if you start answering every support request and every feature request, is going to take all your time and is going to destroy the project ultimately.
So we talked a bit about the TensorFlow paper. There's another paper that came out of Google somewhat recently about machine learning called Machine Learning, the High Interest Credit Card of Technical Debt. Did you read that one also,
Yeah.
I'm assuming?
Yes.
What's your take on that paper? What do you think about it?
So it points out a very important problem, which is that when you are introducing a machine learning model in production, it introduces lots of dependencies, some of them not immediately obvious. So things like the data the model was trained on and so on. And so I think we are starting to develop some best practices for dealing with machine learning models in production over the long term. But because it's still very new, the field is still very much in its infancy, I would say, the field of production machine learning engineering.
What are I don't know if you've been following or if you followed what came out of NIPS, but I'm assuming you followed that as well. Was there anything that excited you that came out of that conference?
In general, I would say you can see several trends that are quite interesting. So things like the fact that we are still making basically exponential progress on all fronts. So we still have not reached this bottleneck of progress that we are probably going to hit in the next few years. So one thing that's interesting to notice is how models are getting bigger and deeper. So we're still in this cambrian explosion of modular architectures.
Why do we assume that we're going to hit a bottleneck?
I don't think everybody assumes it. I do. Simply because we've been making so much progress so fast, it cannot possibly last forever.
Well, it's without precedent, that's for sure.
Yeah, so usually if you look at the progress of science over time, it tends to, you have kind of sigmoidal patterns. So some group of people make some important discoveries, and then following these discoveries, you have like very, very fast progress until you've kind of exhausted the space of potential discoveries that were made possible by the initial discovery, right? And in deep learning, the initial discovery was the realization that, yes, it was possible to train very deep models and bypass, the big problems we had with this at first, so things like vanishing gradients. And once we realized that, and once we developed a few techniques to do that, everything started going very fast. But at some point, we will reach the limitations. We will reach the limits of deep learning as we understand it today, and we will need a new formulation of deep learning, maybe.
Okay, so play devil's advocate against yourself for a moment and assume that we are not going to hit some sort of bottleneck. Like, what if assume machine learning is this, this different kind of science, and the success and progress just continues. How fast are we going? Like, what's on the horizon if we don't hit any bottlenecks?
How fast are we going? In terms of beating benchmarks, we are going exponentially fast. But the thing is, we are just... What we're doing is not necessarily fundamentally different from what we are doing before deep learning. We are just doing it much better in some way. So I don't think deep learning has given us a better understanding of machine learning in general. And, it's not like we're going to come up with artificial humans in the next 20 years, right? We still do not understand anything but the human mind. And some people tend to consider that because we are making very fast progress in machine learning and AI these days, we're going to, like there's a continuity between building an artificial human and, solving these machine learning benchmarks. But there's not, actually. So just because you're making very fast progress on a set of benchmarks does not mean that you're making actually real progress on the fundamental underlying problem, which is the problem of intelligence.
Well, the whole Kurzweilian science behind this, or his hypothesis, is that you don't, we wouldn't be asymptoting towards anything that looks like a human anyway, because whatever is the highest order of artificial intelligence operates much differently than a human would. I mean, that kind of takes us back to the root of our conversation. I mean, if we think about the hardware that the human is built on, then it's not it's different than the hardware that we're building these other first principles on. So I don't know what the implications of that are, but I mean, do you? So in the I guess I'll wrap up with this final question. In the most ambitious, unhalted exponential growth of deep learning, how does the type of artificial intelligence that we would asymptote towards compare to the human intelligence that we have today?
So it's difficult to answer because we cannot really define very well human intelligence, But I can tell you this: what deep learning does. So deep learning is very, very good at mapping some input space to some output space of your choice. So, for instance, if you have a bunch of pictures and then you have labels, then deep learning is going to be very, very good at mapping the two, right? So supervised learning. And but it cannot really do much else at the end of the day. So deep learning is just a very clever way of optimizing a loss function. So wherever you can define a loss function, which is basically going to be this relationship between your input and your output, then deep learning will give you a solution. But that's I think that's very far away from human intelligence.
Mm-hmm. Okay, well that's a good answer. François Chollet, thanks for coming on the Software Engineering Daily. It's been super interesting talking to you about deep learning and Keras, and I'll be following your work closely.
Yep, thank you for having me.